Okay, thank you very much, Bridget. Hello, everybody. Welcome to Jepsen 9, a Fsyncing feeling. That is the official pronunciation for the system call, should you ever need it. My name is Kyle Kingsbury, and you might know me from the internet as Afer. In my day job, I get to break databases, which is basically the coolest thing in the world. But before I broke databases, I was actually an engineer working on APIs. And APIs aren't like regular products or services that you would get in the everyday world. You can't go to the adoption agency and find a cute little API and take it home. You can't buy one at the store. They're services that you sort of behold in the sky and you interact with. You gaze at them and admire them from a distance, but you can never touch. So our API is this illusion, this rainbow in the sky, but it's supported by code. Things written in Ruby or C or Scala. That's these steel girders that are holding up our rainbow. And those girders, in turn, are supported on some wooden pilings, things like the Ruby VM or the Scala compiler, open source libraries that we pull in. And those are rooted in a firm foundation of persistent services that we found basically lying around on the internet, or whatever we saw in Hacker News that week. These databases here represented by the foundation of a pile of tires. And as anybody who has ever worked with a database knows, the pile of tires is usually on fire. And while our operations staff is screaming and trying to fix the problem by pulling the flaming tires off of the pile and shoving fresh tires on, hopefully to replace them fast enough that the fire eventually goes out, we're going to preserve the illusion for users that everything is okay. We want users to be able to make requests and get responses and to perceive everything as fine, even though the system internally is made up of these faulty, terrible components. This process of climbing the ladder of abstraction higher and higher away from the flames below us is known as information hiding and is a core principle of modern systems design. I'm not just thinking about databases. I'm also talking about queues, discovery services. These things strike fear and terror into the hearts of engineers because they do terrible things, right? They get into split brain, where two different sides of the network believe different truths. They get into broken foreign key constraints, where you go to get an object that's referenced in some part of the database, and the thing it references isn't present anymore. Or you have transient temporal anomalies, where you write something to the database, and then you go to read it, and it's not there. You say, wait, did I write it at all? Was that unsuccessful? And then you read it again, and it shows up. Will it still be there the next time? I don't know. So we want to be able to look at these anomalies, which we know are theoretically possible in some models, but understand if they're present in our real-world systems. To what extent do these problems really matter? And the only way, I think, to find out is to go and measure. I am an experimentalist by heart, and I have been working on building measuring tools for distributed systems, the most successful of which is Jepsen. Jepsen is an open-source library for writing tests for distributed systems, and it treats the system as all systems should be treated, as an interaction between an environment and a system itself. The system is going to be comprised of different processes and a network and computers and lots of moving fiddly bits. But together as a whole, they should provide the illusion of some coherent entity like an SQL database or a key value store. And outside the environment, that's all the clients and persistence layers, now other stuff that interacts with the system. And at the boundary between the environment and the system itself, there should be some invariants that hold. For instance, in my house, I've got like 3 cats, right? And every time I open the door, the cats love to run outside. But if I ever see more than 3 cats run out of my door in a row and no cats came back in, that's an invariant violation. It suggests that somewhere in my house there's a hole where cats are coming back in, or your cats are teleporting from outside the house, inside the house. Something's gone wrong. Now, we're going to measure these invariants by running a bunch of clients outside the system. These clients will be simulating actual participants in a distributed system, like pretending to be users at their computers making HTTP requests, or pretending to be API nodes requesting data from some persistence layer. And we're going to run all the clients on the same JVM so that we know exactly what each one does and when. It's important that we do them all in the same place so we know exactly what the temporal relationships are between these operations. Because in some cases, we want to know, are there real-time guarantees about visibility? The database itself will typically be a collection of 3, 5, 7 nodes, probably running Linux, probably communicating over IP, but it could be anything. Jepsen's sort of agnostic as to what we're going to test. And we'll make requests to the database. Now, a tricky bit about this is that we don't necessarily have access to all the tools we would like. if you're going to test an arbitrary database, you might not be able to find a formal specification of its algorithm. So that might rule out using a proof assistant or a model checker. You might want to introduce some sort of annotations or maybe a special static program analysis system that would do symbolic execution or probabilistic execution. But we can't employ those techniques on all sorts of databases if we don't have the source code or if it's not written in a language or a style which is amenable to analysis. So I'm going to back up and take a sort of black box approach. Let's say we know nothing at all about what happens inside the database, and all we get to see is what the clients interacting with the database observe. So have our clients generate randomized operations like write the number 5 or read the current value. And they'll apply it to the system and come back with some result. And that result could be one of basically 3 things. You could succeed, in which case we know the operation took place. It could fail, and then we know that it did not take place. Or it could time out, or crash, or do something else. And this is a tricky thing. A lot of people assume that a timeout or a crash means that the operation didn't happen. But that's not necessarily the case. It could be the operation is somewhere in the network, or maybe it got written to a queue on disk, and when that box reboots, it's going to look at its queue on disk and suddenly re-inject that operation back into the system. So operations that time out might take effect hours, weeks, years later. And we have to plan for that. So in our analysis, we'll treat these as 3 separate contingencies. We'll run these clients concurrently. So over time, we'll build up a concurrent history of each single-threaded client doing multiple operations against the system. And this history is sort of abstract. It just says, hey, I read 3, I wrote 5, or hey, I enqueued this record, and hey, I dequeued this record. It's completely decoupled from the underlying system itself, and we can analyze that data structure as if it were some abstract execution or history of a program. And that means that we can run a checker that maybe tries to find a path through these transactions, and along that path it should make sense. And if it's a linearizable system, maybe that path always has to go forward in time. If it's a serializable system, maybe we can go backwards and forwards in time. If we're looking for snapshot isolation, maybe weaker constraints apply. So depending on the invariance we measure and the type of system we're analyzing, we'll devise different checkers. But all of them will operate essentially on the observable history of systems interacting with clients. So our overall program here is to generate randomized operations, record a history of those operations as they were applied to the system, and then verify that history is consistent with some abstract model, like a key value store. And while this is going on, we're going to get out our big network shears, and we're going to cut the cables. We're going to pause processes. We're going to slip sleeping drugs into their evening tea. We're going to scribble on their calendars and make sure they go to the wrong child's soccer practice. We're going to basically try to make their lives really difficult and make sure that the system obeys all the correct invariants, even under stressful conditions. So, does this work? When we started doing this in 2013 with React, we found that last write wins, the default mode, would lead to lost writes. But you can do safe commutative updates with CRDTs. MongoDB lost data at all levels of write concern. Redis Sentinel went into split brain and threw away all writes on one side of a partition. Cassandra has last write wins loss, and there is no CRDT option. It also had a row-level isolation system that was not actually isolated. It also had a transactional system based on Paxos, which would deadlock forever after like 10 transactions and never run again. And when that bug was fixed, it had a data loss bug due to double applying transactions. NeoGB claimed to beat the cap theorem by buffering all requests in RAM for the duration of a partition. This, of course, is not available. Kafka had an in-sync replica set, the set of nodes which is currently servicing requests, that could shrink arbitrarily to just a single node acknowledging all of your operations. And if that node crashes, then your operations go with it. Zookeeper passed, which I consider something of a personal failing. etcd and console both exhibited stale reads, so you could see data from the past. Elasticsearch lost data in every class of partition we tested. RabbitMQ, like Redis, went into split brain and lost massive amounts of data on one side of a cluster. Aerospike claimed to be an ACID data store, but turned out to be last write wins, so of course it lost writes too. Elasticsearch at 1.5 still lost data in every single test case, however this time it lost less. They patched some of the bugs. In 2015 at MongoDB, we tested again, and they had closed the write loss problem, but we did uncover 2 phenomena, both stale reads and dirty reads, so you can see data from the past and data that never should have existed. Chronos, a task scheduling system, would fail to schedule tasks forever after it lost its quorum in a certain way. Percona XGDB and Galera Cluster, libraries for MySQL replication, had a snapshot isolated system in which snapshots were neither snapshots nor isolated. RethinkDB passed its basic key value store tests, but if you rapidly reconfigure the cluster, adding and removing nodes, during network partitions, you can induce a certain type of bug that could hose the cluster. VoltDB 6.3 claimed to be a strict serializable SQL system, but in fact exhibited stale reads, dirty reads, and lost writes due to multiple bugs in replication. Crate.io, based on Elasticsearch, exhibits all of Elasticsearch's phenomena. So in 2016, it had stale reads, dirty reads, lost and corrupt updates, and also lost inserts. CockroachDB in 2017 exhibited 2 non-serializable anomalies. One of them was a phantom, so you could fail to observe the history of the system in a serializable way. And another one was you could insert one record and get multiple copies of it back. MongoDB, we reanalyzed in 2017, went a little deeper, and we found a fundamental flaw in the v0 replication protocol, which meant it lost data if there was a clock skew. Unfortunately, that bug was also present in the replacement protocol v1, which led to multiple data loss bugs there as well. And now for something completely different. After our litany of fears passed, I'd like to emphasize that many of these bugs, in fact, almost all of these bugs, are now fixed. Vendors have been incredibly responsive in solving these problems. And to some extent, we shouldn't be surprised that there are so many problems, because doing distributed systems is really tricky. So I don't mean to get down on any particular vendor for this. It's just part of the game. But I do want to emphasize that doing a little bit of testing can reveal surprising results. What I'd like to talk about now is some of the recent work I've been doing over the last year in 3 new distributed systems. The first is Tendermint at 0.10.2, which is a transactional replication system with pluggable state machines, and it offers Byzantine fault tolerance. We're going to break this down. It's a bit much. You could think of it a little bit like the Raft consensus algorithm meets a blockchain system. Like Raft, it's going to form a linearizable order of transactions. That means the transactions happen in a total order. So you do 1, 2, 3, 4. You always know that 2 comes before 3, never the other way around. And you're going to group these transactions into blocks and then hook them together with cryptographic signatures so they form a chain of blocks over time. It's also Byzantine fault tolerant, which is a typical property for blockchain systems. And that means that if some of your nodes are like Regina George and they're trying to spread rumors and lies about you, you can shun them so long as you have the cooperation of a legal and law-abiding group of nodes that is greater than 2/3 of the voting power. Finally, it offers pluggable state machines. So it doesn't give you a database. It says, here are transactions. They're opaque blobs. It's up to you to interpret them. So the validators in Tendermint are the programs that actually generate the history of transactions. And then over an RPC mechanism, they will pass you the operations to perform, and then you can interpret them however you like. So you could build a key value store or a cryptocurrency or a, I don't know, cat trading simulator. But the one that we're going to test is called Merkleize. This is a, yes. This is a key value store based on Merkle trees. And we're going to test it with 2 different workloads. One of them is by looking at it as if it were a single register. So we're going to use exactly 1 key at a time. And then we'll do reads and writes and compare and set operations on that register. But the analyzer for that system is in X space. It is NP hard. So to handle higher throughput, which might expose more race conditions, we're going to have an additional weaker test, which is to simply add a bunch of numbers to a set and then try to read it back and make sure that everything we added shows up. And we're going to do that add by reading the current value. We'll add something to that record, and then we'll write it back if and only if it has not changed. This led to a race condition in Merkleize, where if you rapidly mutated one fraction or one path in the B tree on disk, it could decide that it needed to garbage collect that branch even though it was needed by a concurrent update, and that could lead to corrupt state. We tested with clock skew, both by bumping the clock and by strobing it rapidly back and forth by, say, 30 seconds every 15 milliseconds. This is a really interesting thing to do to computers because a lot of times we assume that timeouts will fire approximately on time. And if your clock is strobing back and forth by 30 seconds every 10 millis, it means that all your timeouts are going to fire almost immediately. So that leads to some really interesting race conditions, but it did not break Tendermint. We also tested with crashes. You can kill all the nodes and bring them back, and it works OK. You can isolate single nodes. You can cut the network in half. You can create intersecting rings where every node sees a majority of nodes, but no node agrees on what the majority is, and they all work as well. The one case we found where you could lose data was with duplicate validators. So you run 2 copies of a single logical node, and you let them evolve independently. And this is to simulate a malicious validator who's like promising, oh yeah, sure, George, I'll go to your birthday party on Sunday. And then somebody said, hey, will you get ice cream with me on Sunday? You're like, yeah, I'll go to get ice cream with you on Sunday. You've made these contradictory promises in the logs. But if there's a partition that allows those 2 contradictory promises to only be visible on separate nodes, and the malicious validator has a supermajority, then you can still commit on both sides of the partition and get contradictory blockchains as a result. So when these nodes come back together, they'll realize, oh no, we've been lied to. Node A has signed transactions that conflict, and they'll sort of lose data or kill themselves. But this is somewhat to be expected because Tendermint explicitly specifies you cannot have more than 1/3 of the nodes in terms of voting power be malicious. We tested another fault, which is to kill nodes and then truncate their on-disk logs and then to bring them back up. This simulates cases where the file system might have failed to journal things correctly. This found a Merkleized crash, which is actually in the library GoLevelDB. It turns out that GoLevelDB doesn't do its recovery perfect in all cases. Sometimes if you truncate a write in the middle of the write, it will just explode and refuse to recover. And it turns out this is applied to, several production systems, not just Tendermint. There's also a theoretical vulnerability in Tendermint. Its write-ahead log turned out to not be write-ahead. It was write whenever. So they added an Fsync call, and that fixes that. You can also dynamically reconfigure Tendermint clusters, so you can add and remove validators on the fly, which is a really nice operational property. But it didn't actually result in problems, so I'm really happy about that too. The data corruption and crash bugs are sort of to be expected. This is a very young product. It was still in beta when we were testing. And the Tendermint team has been working to address these issues. Next up, I want to talk about Hazelcast at version 3.8.3. Hazelcast is an in-memory data grid, which is a fancy way of saying data structure server. So it's going to give you the ability to have distributed maps and sets and queues that sort of live in a cloud of machines. And they're not necessarily persistent to disk, but they should be safe so long as nodes keep running most of the time. So you get sets, you get lists, you get IDs, so you can generate unique IDs. You get semaphores and locks for concurrency control. You get distributed queues and atomic longs, so you can mutate some number atomically. All these really nice primitives. Like, this is the toolkit that we want as distributed systems developers. But it's got a tricky problem, and that's that when a network partition occurs, 2 components can run independently. Now, to resolve the conflicts between independent running clusters, you can merge things together. But the merge function isn't necessarily always going to be commutative, so you might lose updates on one side or do something that doesn't quite make sense. There's a split brain protection system, which is supposed to kill nodes on the minority side. This is a common tactic to defend against partitions, but it is never safe because it only kicks in after you've detected the partition, and that could take maybe tens of seconds. The first data type we tested is a lock, and it says that locks are guaranteed to be executed by only one thread in the cluster. So you might assume that you could acquire a lock, run some code, release the lock, and that nobody else would run while you held that lock. This is the way we think about mutexes. Unfortunately, you could see a process acquire the lock, and while it's holding it, 3 other processes could also acquire the lock and go on to hold it as well. So this is the opposite of a lock. It is not a lock. Even if it was a lock, it would be wrong, because even if you hold these things exclusively, the reason you hold the lock is to do some side effects, right? Side effects that go into the network and could take arbitrarily long to complete, so you can't control exclusively what the order would be. This is why lock services and distributed systems don't really exist. Anytime you see one, you should run. Read the Tubby paper for a more nuanced and accurate view of that for a aggressive polemic. Queues say that you can add an item in one machine and remove it from another one. This is how we would like queues to work. So you put in the numbers 1, 2, 3, and 4. They're all acknowledged as successful. And what comes out is 1, 1, 2, 4. So you have multiple copies of 1, which is OK, fine. But you have no copies of 3, which is a little bit troubling. So you might see like 2% duplicated records, 2% lost records. And this actually gets worse with the default timeouts. This is the most aggressive, safe option I could choose. This is with the partition detection, with the quorum stuff enabled, and with short timeouts for everything. There's an atomic reference type and an atomic long type, which says that you can have guaranteed atomic compare and set across the cluster. So I could use this to change a value if and only if it's currently some other value. And those operations should be atomic and never overlap each other. So the way this is supposed to work is that I've got a value like 2, and in the top transaction, I'll read it, and I want to write back 3. So I'm going to increment 2, get 3, and write it back if and only if it's still 2. And that succeeds, because the value is still 2. Concurrently, this bottom transaction will read 2, increment to get 3, and write back, and it says, hey, are you still 2? Oh, I'm sorry, the value has changed, so I'm not going to write. And this ensures that we can do increments in a safe atomic way. We don't lose any updates. But what will actually happen in Hazelcast is that the other commit will also go through. And now we've taken 2 and added 1 plus 1 and gotten 3. So we've clearly not done something atomically. This is fine. This makes a little more sense when you consider that the state of the system has forked into multiple copies. There's some nodes that think the value is 2 on both sides, and you can independently update each of them. And you could continue to evolve. So maybe on one side, you increment, so you get 3, 4, 5. On the other cluster on the bottom, you have 3. And depending on who you're talking to, you could see the value oscillate between 3 and 5, 3 and 5. So you might even see non-monotonic outcomes. And worse yet, when you recover, there's sort of this opaque decision that just chooses a value for you based on some heuristics. So you might see your value go from 5 back to 3, and now you've exhibited in a system that only adds to the number going back in time. I mean, like, what are you doing? Like, look at your life, look at your choices. The whole point of an atomic object is to be atomic. So please, like, use an algorithm that actually does that. You might say, okay, fine, let's back off and try something easier. Let's try ID generation. So you would do something like a flake ID. We know this is coordination free. It gives you updates that are relatively fast. But unfortunately, the ID generator is backed by an atomic long, so it does exactly the same thing. It will increment on both sides, get the same IDs, and hand them out to 2 different people. So you could generate like 834,000 identifiers, but 91,000 of those will be duplicates with each other in a 30-second period. Maps offer these operations like put if absent, and that says like set k to v only if it's not set currently. Or you could replace, say, set k to v prime only if it's currently v. This is like a cas operation and a write, but now it's generalized to maps. And if you think about it, the existence of these functions implies that there is a current singular value for that map. Like, what does it mean to put if absent if the map both contains and also does not contain the object? Right? These concurrent data structures simply don't make sense in the context of these functions. But they're there anyway. They're documented to work. And if you try them, they lose data, even with quorum protection. However, if you use a custom merge function and use compare and set on every independent replica, then you can build CRDTs that merge data back together safely, and you can get commutative updates, but only for map types, as of the time I wrote this analysis. Recommendations in general. If you're writing a distributed system, choose a replication algorithm that is appropriate for your data type. So if you're going to build an atomic long, you know that it needs to be probably sequential and possibly linearizable. Those algorithms require something like a Paxos or a Raft or a Zab. So choose one of those. Don't try to back it by some weaker or eventually consistent thing. For things like ID generation, you can use flake IDs. For counters, you can have eventually consistent counters like PN counters. There's a whole family of algorithms here that might be applicable. If you're a Hazelcast user, you should not rely on Hazelcast for anything that has to do with safety. Like, don't use it as a lock service. But unfortunately, users of Hazelcast can and do use these functions as they're documented without really understanding the consequences. So like the very first thing I saw on the partner blog post page on Hazelcast was BagGreeDB. And BagGreeDB internally generates transaction identifiers using an ID generator from Hazelcast, which means that sometimes it will generate 2 transactions with the same ID. Like, who knows what happens when that occurs? OrientDB used to put all of their cluster state and all their transactional management through Hazelcast as well, and they had so many problems with data loss they backed off. They've almost removed it, but it's still used for the cluster state management. And when I emailed them, and like, what do you mean it can do this behavior? I'm like, yeah, surprise. So look out for these things. Like Hazelcast is commonly deployed as a cache, in which case this is totally fine, right? Caches are supposed to be fuzzy and lossy. But if you're using things like the locks and atomic references, you might want to look twice. Since the time of this analysis, Hazelcast has basically backed off and gutted everything. They've updated the documentation. They have added support for, I believe, flake IDs and new CRDT data types, which is like, great. And I think they're working on a Raft implementation as well. So a lot of this should change in upcoming releases. Finally, anybody who's trying to sell you a distributed lock is trying to sell you sawdust and lies. They're not real. Stop trying to use them. Any locking system is designed to control side effects. So you need to couple the side effects themselves to the underlying system you're testing. This is a whole different talk, but I want to throw it out there. Last but not least, I want to talk about error spike at 39903. We came back and tested this in 2015. It was a distributed sharded document store, which means it's a key value store, but there's some structure to the values. And it claimed to be an ACID data store, but was actually last write wins. So it merged things based on timestamp or based on the number of changes on a single replica. And so, of course, it lost a lot of data during partitions. But they actually went back to the drawing board after the analysis. And they spent the last 2 years gutting and redesigning all of their internals. And so the number of things that come out of this, they've actually dramatically improved the probability of data loss. So the frequency and severity of these issues is decreased. And that's really important because for a lot of users, you're willing to tolerate some degree of loss, but you lose a little bit of money every time it happens. So maybe you're building a machine learning model and it gets less accurate when you drop records. So it turns out that these customers may have developed like sophisticated modeling techniques for deciding, is this enough data or not? And every little bit of consistency you can add helps them do better. So there's already a nice outcome to this. But the other thing they've done is to add a custom consensus protocol. And in 4.0, they're releasing a strong consistency mode, which offers linearizability. And that's what I came in to test. The first thing we found in error spike was that you could start off a test with a completely blank slate, and the very first operation you do is to read 2. It's like buying a fridge from Sears, opening it, and finding like a head of lettuce. Like, where did this come from? Well, if you look carefully at the history, you might see that prior to that there was a write of 2, but it failed. So of course your visualization system, didn't actually render it. And you start to think maybe that failed write of 2 actually took place. The way this happens is that a client makes a request to write 2 to the server, but the server doesn't own the data that you're modifying, so it's going to proxy it onwards to some other server that does own the data, where it gets applied, but the acknowledgement message is lost. So the original proxying server will time out and retry that operation. It issues a retry, and then the remote server says, oh, I'm sorry, I don't accept that write anymore. I no longer own that data. Or some other failure has happened. But it's definitely not happening. I definitely did not apply your write this time. And then the proxying server dutifully relays to the client that the operation failed. What it neglected to think about was that maybe its previous request had actually succeeded. So the thing you want to be careful about in doing proxy systems retries is to make sure that you take the most indeterminate failure state as your return code, so you don't accidentally promise your users that something definitely didn't happen when it actually could have. This is the same bug that bit CockroachDB. We saw you could insert one record, and due to some like sort of uncareful handling of exactly which operations could be replayed and when, you could end up retrying an insert operation multiple times, seeing a definite failure and retrying even though it had actually internally succeeded. So this is a sort of common pattern, I think. This is fixed in 39915. Hooray! So we went on to test node crashes. So we would drop pianos on nodes, and hopefully the rest of the cluster would go about their day. And you could kill one node, and it would work fine. Kill 2 nodes, works fine. Kill 3, it stops working. And this is normal and expected, because most consistent systems work with majority quorums. What you would not expect is that when you restart all of the nodes, it doesn't ever come back. That's a little bit atypical. And in fact, the partition is dead. It's fully dead, and it has to be revived. So you swoop in as the operator, you shout, "Heroes never die!" And you resurrect the partition with an administrative command, but when it comes back, it's not quite all there. Some operations may have been lost. So that's a bit of a problem, and it stems from Aerospike not flushing operations to disk. And this is a documented behavior in Aerospike. For performance reasons, they relied mostly on having multiple copies on different nodes in memory, as opposed to having copies on stable, durable storage. And the idea was that most of customers preferred that trade-off. However, sometimes you really do want durability because you think you might lose every node at once. And so now there's a mode you can enable in 3921 that actually flushes to disk correctly. The other problem we found is that clock skew can lead to lost updates. Inside of Aerospike, there's a metadata record that has like the logical clock for a record and maybe some information about its location. And that clock is comprised of 3 parts. There's a logical regime, which is like the term in Raft. It's incremented every time there's an election. So every leader for the cluster has its own regime. And then there's a node local wall clock on that leader, which is monotonically enforced, and that gives you an order for each regime. And then if you have to do multiple updates inside of the same wall clock, then you use a counter. However, for performance reasons, this entire data structure must fit in a cache line, plus a lot of other stuff, which means that there's very few bits available to squeeze this data structure into. In fact, there are only 6 bits available for regimes, which means that you can only do 32 elections before your regime counter runs out. Now, obviously, most of us will do more than 32 elections in the life of our clusters, and so we will eventually have to reset the counter to 0 and start over again. But when that happens, you could compare 2 regimes and see that a more recent regime actually had a lower number. Okay, how do we solve this? Well, we know that it takes a certain number of seconds to do an election. So let's say that if you've had more than 27 seconds between these things, then you know the regime counter could have rolled over. So if you see a bigger gap than 27 seconds, then we'll choose by wall clock. If we see less than that, we'll choose by regime. And so long as all of our clock skews are under 27 seconds, this is OK. What happens if they're over 27 seconds? It gets a little subtle. Imagine node A is a primary for regime 1, and it receives a write, W1, and immediately pauses, holds onto that write in RAM. Node B detects that node A is unresponsive and has elected a new primary at regime 2 and is able to service writes. So it takes write W2, it writes the number 2 down on disk, and it says, I have 2 at regime 2, and it is time 0. Node A wakes up. And it says, hey, I've got this write 1. OK, cool. So it writes down 1 locally, assumes it's still a primary because it doesn't know any better, and it sends that write W1 over to B. Now, B sees this write of 1 at regime 1 and says, well, I'm regime 2, so of course I'm going to reject this. I'm a more recent primary than you are. And then, of course, A says, oh, I'm sorry, my bad, and forwards that onto the client, but it doesn't actually delete it locally. So on disk, there's still this record of 1 at regime 1 and time 27, because we were asleep. So at some later time, there will be a reconciliation process when these 2 nodes exchange information just routinely to heal anything that might have diverged. And they'll find out that one copy of the record was at time 27, and the other was at time 0. And they'll prefer the time 27 copy from the older regime, which causes us to preserve a failed write and delete a successfully acknowledged one. A bit tricky. I mean, really? Like, yeah, OK, really. Because A, this is a known fault. It's documented in the manual. This is a trade-off that they made for performance reasons to preserve that cache line problem. And they know that as they free up bits in that data structure, they can increase the size and increase clock skew tolerance. And most clock skew is on the order of maybe hundreds of milliseconds to tens of seconds. Only infrequently do you see clock skew of hours, mostly. And so this is mostly OK. And as long as you stay in these bounds, it actually does pass. If you use the durable flag, you stay in clock skew bounds, Aerospike now provides linearizability, which is like a really big jump for 2 years of engineering work. Just keep in mind, if you're a user, that cross-data center replication, anything that does multiple record scans, and user-defined functions haven't been fully integrated into strong consistency yet. That's going to happen in future releases. To recap, when you choose a database as an engineer, you are essentially signing a contract. Even if you use an open source database, right, you're locking yourself into operational expertise, client libraries, a certain way of doing things. And essentially, we are Ariel signing a contract with the vendor, Ursula the Sea Witch. And if we don't read the fine print in the documentation carefully, we might discover that there are certain caveats to using this particular database. Like, if you don't kiss the prince by the third day, then all of your data is forfeit. So we need to read the documentation very carefully to look for these failure modes and understand what we're really getting into. And then throw away all of that information and test it for yourself, because oftentimes the vendors don't know either. Look out for words like strict consistency, acid, strong consistency. If this is the only description you see on a product page, it's a hint that the people who designed it don't know what those words mean. You want to look for a really formal and specific guarantee. Like, acid could mean read uncommitted. That's a level in ANSI SQL, but it's not a very useful one. It could mean serializable. It could mean strict serializable. So try to figure out exactly what the temporal and logical guarantees are around the system. I want to encourage both users and engineers who are building the systems to become a little more formal, become a little more familiar with these definitions so that we can specify exactly what kind of guarantees we need and provide. And then figure out the invariance you actually need, because not every workload requires 100% safety. Not everybody needs to prevent stale reads. Not everybody needs to preserve all data. There are plenty of applications where losing 10% of your writes is perfectly acceptable and, in fact, desirable in the name of efficiency. Finally, consider your failure modes, because it's not enough to test these systems only in the happy case. So try process crashes. Run kill-9 during your test. Try introducing node failure by using your cloud provider or going and flipping power switches. You can also try clock skew with either date or with an LD preload shim called libfakeTime that lies about the clock to the underlying process. You can do garbage collection, I/O pauses with sig stop and sig continue. It turns out that garbage collection or an I/O stall tend to look a lot like a network partition because a process stops responding for a long time, and it could trigger an election. And then that process comes back thinking it's still a leader, but with a past state. We can also introduce network partitions, which I think are the most interesting failure mode. This occurs it's most useful because when you have a partition, the timescales involved are long, right? So in concurrent systems, you're often looking for race conditions, and your window of time is very short. But with a network partition, the message delay times are measured in seconds to minutes, and that's plenty of time for you to reach in there and observe some sort of race occurring. So try IP tables with -j drop all packets from a node, from a client. Try TC for systems that aren't based on TCP. You can introduce probabilistic drops and delays in packets. Ultimately, I want to test systems end to end. Don't just look at the individual systems. Don't think about the database by itself, but also about the composition of the database and its caching service and the API you wrote on top of it. Does the user registration service guarantee that you can only register one username once? Or can you give it out to multiple people? That's an invariant that we care about. And as Tolstoy reminds us, if you look for perfection, you'll never be content. At some point, we have to accept that testing these systems exhaustively is going to be a boiling the ocean problem. We have to accept some degree of failure, but doing a little bit of testing, a little bit of QA up front can dramatically improve things. So I want to advocate for property-based testing. Look for the high-level invariance that your system needs, generate randomized inputs, and then verify the system satisfies those invariants with distributed systems failure modes. This would not have been possible without the financial assistance of Tendermint, the assistance of people at Hazelcast, including users like Jordan Haltman, Luigi Dell'Aquila, Luca Garulli, and Denis Sokoroslov. Aerospike funded the research on their database, and Peter Alvaro has been my tireless research advisor from UC Santa Cruz. Thank you to Bridget and everybody at GOTO for inviting me, and thanks for your time. If you want to learn more about this research, you can go to jepsen.io, where there's comprehensive write-ups and links to the source, and I will be happy to take a couple questions.
Great. Quick round of applause. Wonderful talk, Kyle. And I imagine a few people may have a few questions, or they've all just had their minds blown and are saying, oh, I have so much to do now. But curious if I have people who have questions. Everyone is like, I have so much I need to do now. I actually do have a quick question to start with, which is, you showed us a lot of things that are kind of terrifying. And then you mentioned that people need to kind of figure out where the right constraints are for them, how much terrifying data loss is okay for them. How would you advise people even start to figure out what the answer to that is for them?
I feel like figuring out how much data loss is okay is sort of an unsolved problem. And we still don't know, in distributed systems research, can we guarantee safety with weaker isolation levels? Like, is your workload okay on read committed, or do you need serializable? That's an open problem. There's some work in specification languages towards it, but we really don't know. And moreover, it's also a probabilistic problem, right? So you need to develop a model of how often your nodes fail, how often network partitions occur, what your clock skews are. And these things require both observation and statistical modeling tools. People do this. I know at least one group in ad tech that does rigorous modeling of their failures. And I have a hunch that a number of banks do it too. But I don't think it's like an industry-wide standard yet.
Interesting. So an area for future work.
So what's next? Can you give us a preview of anything that you're working on or like coming out with? Can you give us a preview of anything that you're working on right now? It's coming up.
What is next? What am I working on right now? I am churning out analyses as fast as I can possibly go. And I'm also working on a couple research projects. One of them is I have a generalized checker for linearizability. I can tell you, is any data structure that you like to specify supported by this underlying system? You can write a queue, you could write a key value store, you could write an SQL table, whatever you like, and I can check it for you, arbitrary transactions. But what I can't do is that for serializability. And I can't do it for snapshot isolation. So I'm trying to devise checkers that will efficiently verify these properties on weaker isolation levels. And the state space is exponential for the easy problem, and it's even more exponential for these other problems. So I'm still trying to work my way up to that.
That is awesome. Okay, we're just about out of time, but we first, let's give another round of applause to our wonderful talk, Kyle Kingsbury.
Thank you.